So here we're given a function, f of x, and it's a quadratic in vertex form, and we have to find f inverse of x algebraically, and then graph both of these functions. Now, we kind of intuitively know that we're going to have a radical function as our inverse, because radicals will undo squares. So step one is we start by writing out the inverse identity. That's f of f inverse of x is equal to x. And that's because if you apply a function and its inverse, you should get the variable that you used. So what we have to do is we have to substitute this entire f inverse expression in place of every x in the function. Unfortunately, there's only one. So we'll do that. We'll have 1/3 of f inverse of x minus 2 squared plus 1 equals x. So all we've done is replaced the x with the f inverse of x. Now we'll do some algebra. So we're looking to isolate the f inverse of x portion. So we'll subtract 1 from both sides. That will leave us with x minus 1. Those ones will cancel. We'll multiply both sides by 3. And that will leave us with 3x minus 1. And the 3 and the 1/3 will cancel. And we'll be left with just this portion and the square on the left side. So we'll have f inverse of x minus 2, and the whole thing is squared. Now, to get rid of the square, we have to take the square root. So we'll take the square root of both sides, and we'll get f inverse of x minus 2 equals the square root of 3x minus 1. The last step is to get rid of this 2, so we'll add 2 to both sides. The 2's will cancel, and I've now found f inverse of x as the square root of 3x minus 1 plus 2. And this plus is outside of the radical. Now, if I'm going to graph both of these functions, it's important to note the domains. So the domain of our quadratic, so f's domain, is the set of all real numbers. And that's because we can square any real number. But f's range, because this quadratic opens up, is everything greater than the point where its vertex is. And its vertex is at 2, 1. So the range of f is a set of all y such that y is greater than or equal to 1, and y is an element of the reals. Now, when we graph f of x, we need to exchange the domain and the range. So f inverse of x's domain is going to be identical to the range. So it'll be x such that x is greater than or equal to 1, and x is an element of the reals. And its range will be y is an element of the reals. But the thing is, we know that we have a set restriction on this function. On this function, we know that x cannot be less than 1. We also know that this function only has one portion. So it only has a portion going from its starting point. Here it's going to be 1, and it's everything to the left of 1 is not going to be allowed. When we look at a graph of the two things, and I'll do a very quick sketch of the graph, we're going to notice that we're missing a slight portion. So I'm just going to set up a very quick graph here. Y, X, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And if I were to graph the original function f of x, I know its vertex is at 2, 1, 2, 1. And it goes over 1, up 1/3. Over 1, up 3/3. Over 1, up 4/3. And I know that it's symmetrical about its vertex, so I can actually go ahead and plot the rest of the points. This would be minus 1. So this would be the function f of x. And now recall that when we graph inverses, we're just graphing a reflection in the line y equals x. And the line y equals x looks something like this. So this would be the line y equals x. So every point on f of x should be a point reflected to f inverse. So this point at 2, 1 would reflect to 1, 2. And this point at 3 and 1 1/3 would reflect to 1 1/3 and 3. And this point at 5 and 4 would reflect to 4 and 5. And we would end up getting that portion. Now this is what is known as one branch of the inverse. The other branch of the inverse goes down and through so that we see the reflection of the parabola. But if we include this branch, that is, if we include everything below this line on our inverse function, then our inverse is no longer a function. So it's often that you'll hear about restrictions being added to inverses, so that way the inverse is a function. Here we can see it's not, because it clearly fails the vertical line test at all of these values of x. And so we've now algebraically calculated the formula for f inverse. We've plotted f inverse, realized that it's not a